Hello, and welcome to Know It Training's software course. This course was designed to help you develop a fundamental understanding of software. In this course, you'll learn about the different types of software and what they do. You'll also see how software operates as a bridge between users and computer hardware to make computers perform specific tasks. Then you'll learn about the software development lifecycle, the step-by-step process for developing software. Software is nothing more than a series of instructions written in a programming language like C++, Java, Perl, or PHP. These instructions are commonly called code. It is software that makes your computer come alive in many ways. Software displays images on a screen. It asks us for our login ID and password. It lets us type and print a letter using Microsoft Word, and lets us perform calculations using an Excel spreadsheet. In 1834, a brilliant Englishwoman named Ada Lovelace wrote a set of instructions that is considered to be the first computer program. Here's a picture of it. Writing this program earned her the title of the world's first computer programmer. Just looking at it, you can imagine how difficult and time-consuming it was to create. Fast forward 100 years later, and writing software hadn't gotten much easier. You see, computer hardware only understands a language called binary code, which is simply made up of ones and zeros. In the early days of software, computer programmers wrote programs in binary, a very tedious and complex task. Today's programming languages are a far cry from binary. Languages like C++, Java, and Perl use commands that are more familiar to the English language, such as return, add, and print, rather than ones and zeros. These programming languages are called high-level languages because they are similar to actual spoken language. The big question is, how does hardware that only understands ones and zeros execute instructions or code written in words similar to our spoken language? Let's take a look. Modern computer technology is built on a 4-layer model. Those layers are the user, application software, system software, and hardware. Each layer serves the layer above it and communicates with the layer above and below it. Let's start at the bottom layer, hardware. Hardware is not software, it's hardware. But hardware is indispensable to software. Software can't actually do any processing of information or data. Only hardware can. The hardware of your computer is made up of several hardware components. The central processing unit, or CPU, is the brains of your computer and does all the processing of data. The CPU can only perform one operation at a time, which is hard for most people to believe because lots of things seem to be happening all at one time. That's because the CPU can perform several billion operations per second, much faster than humans can perceive them. Another piece of hardware is the hard drive, or hard disk. The hard drive is your computer's permanent memory. If you turn your computer off and then back on again, the information stored in the hard drive will still be there. This is because the hard drive does not require power to keep things stored in memory. The hard drive uses tiny magnetic particles on a spinning disk to store the information. As the disk spins, a head turns the particle one way to represent a 1 and the other way to represent a 0, so the data can be stored in binary code. Compared to the CPU, the hard drive is relatively slow because it's limited by the speed of mechanical moving parts. Another component of your computer's hardware is RAM, or random access memory. RAM is temporary memory and is purely electrical, requiring power to store information in memory. If you turn off your computer, anything stored in RAM disappears. RAM is not bound by the speed of mechanical parts, but rather by the speed with which electricity flows, which is close to the speed of light. For that reason, RAM is much faster than the hard drive. All of these hardware components are connected by buses, which are sets of parallel wires that allow data to flow between the hardware components. Now let's look at how these hardware components work together to process information or data. When a computer user wants to work on a Word document, the necessary files are moved from the hard drive to RAM as a stream of ones and zeros. Since RAM is much faster than the hard drive, it can feed the data in these files very quickly to the CPU. The CPU does all the processing of the data and sends it back to RAM. When the user saves the document, the files are moved back to the hard disk to be saved in permanent memory. All of this activity is managed by system software. System software is what makes the hardware do what is needed and runs all the operations of your computer. System software comes in the form of an operating system, or OS, such as Windows, Mac OS, or Linux. At the heart of the operating system is the kernel, the part of the OS specifically designed to work with your computer's particular hardware. All of the communication from other parts of the OS go through the kernel to speak to the hardware. If you plug in a new piece of hardware, such as a flash drive, the operating system will go out and find a driver for the flash drive. That driver then tells the kernel how to communicate with that new piece of hardware. Another part of the OS is the scheduler. The scheduler determines the order in which the CPU performs tasks. In the example we just looked at, only Microsoft Word was in use. But computer users often have several programs running at the same time, and each is asking the CPU to perform different tasks. So the CPU does a little of each task, going from one task to another, until all the tasks are complete. The scheduler coordinates all of this activity. Another component of the OS is the file manager, the part of the OS responsible for helping the user organize files into folders, which are also called directories, and for moving files around. In our previous example, it was the file manager that was responsible for moving files from the hard disk to RAM. At the top of the OS is the OS interface. The OS interface is the part of the OS that communicates with the application software. Application software must be written to run on a specific OS interface because the Windows interface is different from the Linux interface and the Mac OS interface. Application software is the software that users interact with every day. Some examples of application software are Google Chrome, Microsoft Word, SAP. They do things real people want to do, like type a letter, access customer records, or search for information on the internet. Application software interacts directly with the user, usually through a graphical user interface, or GUI. The GUI is the part of the application software that displays information on your computer screen and allows the user to input information, like login IDs and passwords. Below the GUI is application software that handles business logic. That's the part of the software that enables a program like Excel to calculate averages or allows you to design your own car on Ford's webpage. Application software, or apps, are written in high-level languages like C++, Java, and PHP. Although application software is written in high-level language like C++, when it's running inside your computer, it's been changed into binary. This is done by another component of the OS called a compiler, or interpreter. C++ code goes into a C++ compiler, and it is translated into binary so that all the parts of the computer can use it. If you've ever heard a programmer talk about compiling code, this is what they're talking about. At the top of this software stack is you, the user. Without a user, neither software nor hardware would have any purpose. As I mentioned earlier, each layer serves the layer above it. But since all the processing of data takes place in the hardware, ultimately both application software and system software only exist to make the hardware perform tasks required by the user. Here's an example of the four-layer system in action, from top to bottom. When a user opens Microsoft Word, Word's GUI displays menu options to create or load an existing document. When the user selects an existing document, the GUI communicates the user's action to the business logic. The business logic then makes a call to the OS file manager through the OS interface. The file manager issues instructions through the kernel to transfer the necessary files from the hard drive to RAM. which is then displayed on the computer in the form of a Word document. This is basically how a computer works. Now let's look at how software is developed. Software development means computer programming, or writing code. But the overall process of taking an idea and turning it into quality software can be viewed as a process, a series of steps to follow to accomplish the job of software development. This overall process is called the Software Development Lifecycle, or SDLC. The software development lifecycle is a set of phases that begin with the requirements phase. The requirements phase is all about understanding what the new software is supposed to do. It's called the requirements phase because during this phase, the needs of the users are translated into requirements, which are the things the users require of the software. The next phase is called the design phase. In this stage, it is decided how the software will work. In the design phase, software architects and technical analysts use the requirements to develop the overall structure of the software, called the software architecture. In addition, the architects and analysts will create what's called the software specification, a more detailed description for the programmers of what the software is expected to do. Together, the software architecture and specifications tell programmers what they need to know to develop the software. After the design phase comes the coding phase, sometimes called the implementation phase. This is the phase where the programmers use the software specifications to guide them in writing the software, or code. Believe it or not, coding is often the shortest phase in the development lifecycle. As mentioned earlier, this is also called the implementation phase. When developers talk about implementing solutions, they are simply talking about writing software. Next comes the testing phase, sometimes called the verification phase. Software testing is an investigation of the software to ensure that it meets the requirements of the users, works properly, and can be installed and operated in its intended IT environment. If problems are discovered during the testing phase, the testers send the software back to the programmers, along with their test results, so that any problems with the software can be fixed. The software then goes back through the testing phase. Once the software successfully passes the testing phase, it is put into use and enters the maintenance phase. This is the final phase of the software development lifecycle. In the maintenance phase, someone is responsible for maintaining the software and fixing it when it stops working correctly, or when errors are detected. Like any other product, software can break. The maintenance phase is a continual process, as there is always the possibility that the software will break from time to time. The maintenance phase lasts as long as the software is still in use. Over the years, various approaches to the software development lifecycle have been developed. There's no one-size-fits-all approach to software development. Instead, there are several different methods, or software development methodologies. Two of the most widely used methods are the waterfall model and agile development. Let's take a look at each one and see how they differ. The waterfall model is one of the oldest models of software development, dating back to the 1970s. This had been adopted by many large companies. It's a traditional engineering approach to developing software. The roles of the members of a waterfall project are the business analyst, the team member who is responsible for meeting with users to understand their needs and creating software requirements, the software architects and technical analysts who develop software architecture and specifications, the developers who create or write the software or code, the software tester who tests the code, and the project manager, whose main task it is to manage the project and subdivide tasks among team members. He or she is responsible for the quality of the final software. In the waterfall model, a project is divided into distinct phases that typically look a lot like the phases of the software development lifecycle: requirements, design, coding, testing, and maintenance. In the waterfall model, development is seen as flowing steadily down through all phases, like a waterfall. Waterfall uses the documents that are created during each phase to control the project. Those documents, such as the requirements documents and specifications, are considered as contracts, and once approved, will not change for the rest of the project. Waterfall focuses on strictly following the established development plan as the way to keep the project on track. The downside to the waterfall model is that it assumes everything that needs to be known about a project can be known up front, but in reality, users often can't tell you exactly what they want until they see some sort of example or prototype. This means that requirements that were developed early in the project may not be quite right. Historically, the classic waterfall approach often leads to large portions of the project having to be redone because it wasn't quite what the users wanted. The result can be a project that goes over budget and finishes behind schedule. Because of this, the waterfall model is seen now as a better match for smaller projects and has led to the rise of newer models that attempt to fix some of the problems with waterfall. One of these new models is Agile. As the name Agile development implies, it was designed to be agile and flexible. The Agile approach to software development is fairly new. Its origins can be traced back to February 2001, when a group of top software development gurus met at the Snowbird Resort in Utah to discuss more flexible ways to develop software. The outcome of this meeting was something called the Manifesto for Agile Software Development. While there are now a variety of agile methodologies, with interesting names like Kanban and Scrum, all agile methods adhere to these key principles. Working software is more useful and welcome than just presenting documents to clients in meetings. Requirements cannot be fully collected at the beginning of the software development cycle, so continuous customer or stakeholder involvement is critical. Agile methods focus on quick responses to change and continuous development. Unlike the waterfall model, changes in requirements are welcome, even late in the process. Now let's take a look at Scrum, an agile methodology. The roles in Scrum look a little different from those in Waterfall. They are the product owner, the person responsible for defining the features needed in the software, the development team, programmers, testers, designers, writers, and anyone else who has a hands-on role in software product development, the Scrum Master, the person responsible for keeping the Scrum process consistent and clearing organizational roadblocks for the team. A Scrum Master is sometimes called a project facilitator. And the stakeholders, those with an interest in the product, like users and department heads. Rather than trying to write all the code and test it all at once, Scrum takes a very different approach. With Scrum, the project is broken up into smaller pieces, which contain a small number of items, usually 5 to 10, that can be developed together. They are developed in sprints, or mini projects of 1 to 4 weeks in length. Each sprint starts with a planning phase, where just enough planning is done to develop that small list of items. In the build phase, the team builds what was planned by writing working software. Each day, the team has a stand-up meeting of no more than 15 minutes. In this daily meeting, the team discusses what they did the day before, what they will do today, and any roadblocks that have been encountered. It's called a stand-up meeting because everyone literally stands during the entire meeting. Next is the testing phase. In the testing phase, the team tests the items developed during the sprint. The final phase is the sprint review. During this phase, the team reviews the developed items with the stakeholders. In the sprint review, the stakeholders are being shown working software. During the sprint review, stakeholders provide feedback which may cause changes in the requirements. Remember, changes in requirements are welcome, even late in the process. The development team also uses what they learned during the sprint review to make improvements for the next sprint. The team completes one sprint after another, always looking for ways to improve and respond quickly to change until the entire project is complete and all the software is finished. That's the end of this course material. You just learned what software is and how it works. You've seen the different types of software and learned about their functions. You've also seen how software operates as a bridge between users and hardware to make computers work. You've learned about the step-by-step process for developing software, called the software development lifecycle. You've gained an understanding of the two popular software development methodologies, waterfall and agile, and have seen how they accomplish the task of software development. We hope you've enjoyed this course. In our next course, Virtualization and Cloud, we'll learn how the relationship between hardware and software has changed and how this change has led to an amazing breakthrough in technology called virtualization. See you next time!